Hello everyone, and welcome to the Institute of Physics East Midlands Branch Prestige Lecture 2020. My name's Rebecca Dewey and I'm the chair of the branch committee. We organise these prestige lectures each year and have recently hosted speakers such as theoretical physicist and science communicator Jim Al-Khalili, planetary scientist and aspiring astronaut Susie Imber, and writer, comedian and broadcaster Tamandra Harkness. This year we were expecting to host this lecture at Nottingham Trent University in Nottingham City Centre, but due to the obvious, our plans have changed somewhat. We're absolutely thrilled to take advantage of the new situation and bring this lecture to so many more people, spanning a much wider geographical range, and all from the comfort of our and your own living rooms. Jocelyn Bell Burnell is an astrophysicist, best known for her discovery in 1967 of rotating neutron stars that appear to pulse, which have since been coined pulsars. Jocelyn had originally set out to study the recently detected star-like quasars, but found in her data a signal that pulsed once every second and called it the Little Green Man 1. Her discovery is considered to be one of the greatest in 20th century astronomy. Jocelyn has since become a hugely influential role model for young female scientists, including myself. She became Commander of the British Empire for her services to astronomy in 1999 and a Dame in 2007. I'm super excited to be introducing her tonight to give her lecture entitled Bursts, Bangs and Things That Go Bump in the Night. For anyone who would like to receive this lecture in British Sign Language, we have a BSL interpreter, Elvira Roberts, signing for you this evening. You can click and drag the bar between the people's videos and the slides to make Elvira and Jocelyn bigger or smaller. There will be an opportunity for me to read out some of your questions at the end, so please get your questions coming in the chat. This lecture, together with the BSL interpretation, will be recorded and posted online for future access. Over to you, Jocelyn.
Thank you very much, Rebecca. Am I heard okay? I shall take the silence as being yes. Thank you very much. So I want to talk tonight about a very new topic in astronomy. It's changing week by week. It's incredibly exciting. And it's an area where there's a lot we still don't understand because the data, the amazing things are still rolling in. It's the field of transient astronomy. Now, can I move the slides on or does somebody do it? Aha, thank you. So this lovely picture was taken by the Hubble Space Telescope. It's known as the Hubble Deep Field. And to take this picture, Hubble stared at this one patch of sky for 143 hours. It's a very tiny area. If you held a tennis ball 100 meters away from you, the size of the tennis ball would be the same as the size of this bit of sky. But because we're staring deep, we can see many, many distant things. We're seeing some objects that are 12 billion light years away. One of the things that really interested astronomers about this field was that there's still blackness, black space between the objects that shine. Most of the objects that shine are galaxies. There is one star just a little bit left of center. You know it's a star because you can see it's got spikes through it, a cross shape of spikes. That's actually produced in the telescope. And it only happens where the object's very, very compact. A galaxy doesn't give those spikes. Everything else in that image, I think, there might be one other star somewhere, but everything else is a galaxy. And one of the things that was of interest to the astronomers were that there were galaxies that far away in space and that far back in time. Can I have the next slide, please? Thank you. Now, while staring deep like that, having a long, long stare clearly produces a lot of interesting results. There are some things you are prevented from seeing by that kind of stare. Anything that flares, that changes its brightness, flares or dims, eclipses or flares, you're going to miss that information because it's going to get averaged out over the hours and hours of the stare. We also miss anything that moves, a comet, a planet, an asteroid, things like that, because that just comes out as a slightly blurred, slightly cigar-shaped image. So although staring deep gives us a lot of good science, there's some good science that it doesn't give us. And until very, very recently, we have very little information about things that flared and died, and very little information about things that moved, at least from the big telescopes. Can I have the next slide, please? So what we're going to do in this talk is, in effect, move from stills to movies. Movies are actually a sequence of images taken very short time intervals apart. And with an exploding firework like this, you can see the movement of the bright spots. You can also see changes in the light levels, so flashing or dimming, as well as the movement. And those are the things that we're going to be emphasizing in this particular talk. And the next slide, please. So up till now, we have largely ignored what we call the dynamic sky, things that move, things that change brightness. There have been some parts of astronomy where that statement is not true, pulsar astronomy. X-ray astronomy frequently deals with objects that change their X-ray brightness, and gamma ray astronomy also. So people who work in those fields, along with people who are interested in supernovae or novae, exploding stars, or variable stars, they will be aware of the dynamic sky. But a lot of the big telescopes have been doing deep surveys, and we've blurred out all this dynamic stuff. Thank you. And the next slide, please. Good, thanks. So one kind of transient phenomena that you're probably already aware of is what we call supernovae. Supernovae are supernovae. And novae or nova means a new star. So supernova is a star that was originally very, very faint, maybe invisible, which explodes and becomes visible. We believe that in these supernovae, the core can become a pulsar or a neutron star. In February 1987, we were able to observe a relatively nearby supernova in the Large Magellanic Cloud, and that has been much studied, well studied. Can we move to the next slide? Yes, this is the supernova. It's the very bright spot on the bottom right. Thank you. For a long time, we had no sign of a pulsar in the middle, no pulsations. We still don't have pulsations, but we now have some indication that there is indeed a compact star, a neutron star, in the center of that remnant. And the next slide, please. So using the large millimeter telescope in Chile, the Atacama Large Millimeter Array, which they were using for looking for hot dust, some astronomers, including Mikako Matsuo from Cardiff, got this picture that you can see on the left-hand side. We're looking at the stuff in the center of the ring, and it's enlarged on the extreme left, and it's dust that's shining in millimeter wavelengths. And there is this particularly hot spot just where we would expect a neutron star to be produced in that supernova remnant. So as of a month or so ago, we now actually have evidence that there is a compact object at the center of that remnant. Still haven't seen pulsation, so it may not be pulsating, or maybe something else is going on. So turning now to the monitoring and the searching for things that vary, transient things. At optical wavelengths, a number of older telescopes have been repurposed. The one on the extreme right is a Schmidt telescope owned by Uppsala University that's in Australia. In the centre is the Palomar telescope, old Palomar's telescope, now known as the Vici telescope. And on the extreme left is the Atlas telescope, which is in Hawaii. It's specifically concerned with looking out for asteroids that might impact the Earth. So it's going particularly for moving things. So there's now quite a few telescopes involved in this kind of work. And if we could go to the next slide. So have we skipped a slide? Can we just check? Go back one? No, we haven't skipped a slide. Okay, thank you. Using that Vici facility on the Palomar telescope, they're doing something like this. You take two pictures of the same patch of the sky. And here you will recognize that we're dealing with negative photographs. The stars and galaxies, the bright thing, come out as dark dots, and the dark sky comes out as a pale grey. It's easier to see the stars working with negatives. If you observe a patch of sky, maybe make several observations in fairly quick succession, then leave that patch of sky, go somewhere else, come back to the same patch of sky after 28 days. Why 28 days? Because of the moon. If you come back in 28 days, you'll have the moon at the same phase, and there'll be the same amount of stray light. So with this pattern of observations, which is called the cadence, we're now monitoring a lot of the sky. If you find something's changed, like in this pair of photographs, you see on the right-hand side, there's an extra object in the middle of the field of view. All the other ones are there, but there is one more as well. And it's important that you announce any changes like this quickly so that other telescopes can go look at that object and between all the telescopes, maximize the information we get. Thank you. So going back to Mount Palomar and the Vici, they have fitted a new CCD camera on the old 48-inch telescope. It's a very, very fast camera, works simultaneously in 3 optical bands and goes to 20th magnitude. It started work in 2018, so it's been going now for best part of 3 years. It scans the sky completely every 3 days, and it's looking particularly for things that vary in brightness. And it's finding, for example, more than 10,000 explosive transients, things that suddenly brighten up each year. It is getting 4 terabytes of data every night. That is one hell of a lot of data. And so the processing has to be done by a computer, machine learning. And after 3 full years, it'll have over 3 petabytes of data. So getting the machine to do the processing is very, very important. In a typical night, it produces 1 million alerts. It says, here's 1 million things which have changed since the last time I looked at this bit of sky. It's finding new supernovae and new asteroids every night. It's finding a tidal disruption event, which I'll talk about a bit later, every month. And it's also doing a lot of work on supernovae, that's the exploding stars, how they interact with their environments. The next slide. I'm going to talk now about a phenomenon you might not have heard of called microlensing. And I'm going to start by explaining what it is. So if we could have the next slide, please. So we're on the Earth at the left-hand side of this picture. We're looking at our favorite star, which is over on the right-hand side of the picture. And because all the stars are moving around, each in their own way, it so happens that another star gets between us and our favourite star that we're observing. The gravity of that intervening star bends some of the light rays and bends them into our telescope. Light rays that would normally not reach the Earth get bent down and focus on the Earth. And so while this intruder star is placed exactly between us and our favourite star, we see our favourite star as brighter. We think it has brightened, unless we can see the intruder star. It acts a bit like a lens, and it's due to the gravity of that intruder star. This mechanism also helps us see foreground objects that we weren't aware of if they cause this brightening. So suppose now we have as the foreground object in this particular diagram, and in some of the frames it has a planet. But in the extreme left-hand frame, there's no sign of the planet. There's just the yellow star that we're trying to observe, the red star that comes between us and it, and temporarily makes the yellow star seem brighter. And the little graph at the bottom of the left-hand panel shows how the brightness of the yellow star increases and drops again. Now suppose our red star has a little brown planet. And this, we're in the second panel. We see the brightening due to the red star, and because the little brown planet happens to be falling afterwards, after the red star brightening is decaying, we get another tiny blip of brightening due to the planet. And we can say, ha, that red star has a planet. And it's one way of finding planets that we might not otherwise see. The planet can trail rather further behind the red star, and in the third panel, we see the brightening due to the red star, and then the little blip due to the brown planet. But they're close enough that we link them. But what has happened is shown in the fourth panel. We sometimes see the blip due to the little brown planet, and there is no star anywhere to be seen. The planet is on its own. It's sometimes known as an orphan planet or a free-floating planet, or if you're a negative frame of mind, a rogue planet. But I think labelling it as rogue is a bit unfair. And we've now found that there are about 20 of these orphan planets, and probably many, many more. We're finding them quite fast. Go to the next slide. So at this point, I'm going to move away from the optical part of the spectrum to some of the other wavelengths, other frequencies. The optical bit is that tiny rainbow in the middle. That's the only bit that our eyes are sensitive to. We do not see any of the other frequencies that there are. For example, to the right of the little optical bit, there's ultraviolet, and then X-rays, and then gamma rays. And to the left of the little rainbow going out the red end, there's infrared, millimeter, and radio. And now at many of these other wavelengths, we're also working on these transient objects, things that come and go. And the next slide, please. So I'm going to start by talking about transient gamma ray events. Gamma rays were the extreme right-hand end of that spectrum, you recall. And the next slide. There's an interesting story behind this. The USA signed a nuclear test ban treaty with the USSR. I think this was 1957. It was that there would be no nuclear tests in the Earth's atmosphere. The USA was not convinced that the USSR would comply with this treaty, and so they decided they had to do some monitoring. And a nuclear test in the atmosphere would produce a short burst of gamma rays, so they put up some satellites with gamma ray detectors on them. And they put up several satellites so that if they saw something, they could get a fix on where it was coming from and say, aha, naughty Soviets, you did a test in the atmosphere over the USSR or whatever. And they found some spikes, some bursts of gamma ray emission, and they started trying to position them. Were they coming from over the USSR? Where were they coming from? And they were forced to conclude they were not coming up from the Earth, but down from the sky. Something out in the universe was emitting short bursts of gamma rays. The image shows a more recent detection of a gamma ray burst. You can see it lasts for a few seconds, and while it's there, it's the strongest thing in the sky. You cannot miss it. The scientists had to wait quite a while before the military would agree they could publish these results. So it wasn't until 1973 that we started learning about gamma ray bursts. And the next slide, please. So they've been studied a lot, still are studied. We see about one gamma ray burst every day, and they seem to come from all over the sky. The diagram on the right, the oval, is a plot of where gamma rays have come from against their brightness. And you'll probably agree they're pretty randomly, evenly spattered over the sky. They don't seem to be concentrated anywhere. Now, you might expect to see some extra from the Milky Way, and that would show as a band across the middle. But there's no band there. There's no sign of the Milky Way. So either these things come from very, very nearby the Earth, and so concentration to the Milky Way doesn't matter, or they come from way, way outside the Milky Way, so of course they don't concentrate to the Milky Way. And this was a big debate for a very long time. Are they very near or very far? The next slide. They discovered incidentally that there actually seem to be two kinds of gamma ray bursts, short ones and long ones, with the breakpoint at about 2 seconds. They had actually discovered two different phenomena, and I'll talk later about where these gamma ray bursts come from, and long bursts and short bursts have distinctly different origins. So that was two discoveries in one from some very cheap satellites, which was pretty good going. The next slide. So the long gamma ray bursts, ones that are more than 2 seconds long, they're thought to be due to the collapse of a high mass star. It shrinks way, way down to make maybe a neutron star, maybe a quark star, or maybe a black hole. And as it shrinks down, it produces a very narrow jet of gamma rays. And if that jet happens to point to the Earth, we see a gamma ray burst. Clearly, there'll be quite a lot we don't see. I'll be talking about where the short bursts come from right at the end. Now, the debate about where these bursts came from raged for a long time, and ultimately people got notified in time and they managed to find a bit of an afterglow in the optical. Two photographs here before and after, taken with different telescopes, so the background shows different amounts of graininess, but you can see they're negative photographs, you can see the main objects. And in the right-hand photograph, there is a new image at the tip of the arrow that wasn't there before. And this has appeared at about the same time as the burst, and it's in the right direction. Anything inside that circle could be causing the burst. So it's reckoned that this is what caused that burst, that long burst. And it's a distant galaxy. And we now think that there'll be a few bursts per galaxy per million years. Since we've got a lot of galaxies in the universe, that means we'll see quite a few. Another source of transient events is what's called tidal disruption events. And it works like this, as shown in the next slide. So we have a black hole near the center of the diagram, we have a star, top left, which is on a track to bring it uncomfortably close to the black hole. And it gets pulled in by the gravity, and it also gets distorted into a cigar shape by the gravity, or the gradient of gravity. And then the cigar breaks up into lots of bits, and each of those bits fall into the black hole independently. So it goes plop, 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 plop. And we get a sequence of optical flares or gamma ray flares or X-ray flares or radio flares from close to the black hole. We may also maybe get gravitational radiation, but we haven't found examples of that yet. So far, about 60 candidate events have been seen. Thank you. And the next slide. So I'm now going to talk about what some radio astronomers have been seeing in particular. The next slide. So we're going to the left-hand side of this diagram. Not too far left, not extreme left, but quite a way left. Thank you. Next slide. Good. Right, a little bit of physics here, so as you understand what the radio astronomers are seeing. You've probably seen a rainbow. You may have also seen light dispersed by a prism, like in this diagram, giving a rainbow of colours, the red through to the violet. This happens because in a raindrop or in a glass prism, the different colours, the different wavelengths, travel at different rates and end up spread out. There's something similar happens with radio waves. Can we go to the next slide, please? We're going to listen to an audio file, and then I'll tell you what you're hearing. You'll hear quite a bit of crackle, but you're listening for a whistle, a descending whistle. Don't think it's working terribly well. Never mind, I will whistle it. Apologies to Elvire, I don't know how you're going to do this. So with looking at this diagram, there's a bright band, a vertical band, that would sound like there's a lot of static, which is just, and then in the midst of it all, there's this descending curved curve, which would sound like, and it's called a whistler because it whistles, starting at high frequencies and going down to low frequencies. What has actually happened is there's been a lightning stroke on the other side of the Earth, and that generates a sharp radio pulse, which travels round to us, making a big loop, probably following the magnetic field lines. And as it travels, it passes a number of free electrons. And these free electrons will slow the lower frequencies. The higher frequencies will travel faster. The lower the frequency, the more it gets slowed. And so what started out as a single ends up with the high frequencies first, then getting lower and lower and lower, this descending whistle. Thank you. Now, I seem to be jumping around, but there is some coherence to this. I'm not going to talk much about pulsars tonight, but there are these very small stars, small dense stars, neutron stars, spinning very rapidly, and they sweep a beam of radio waves round the sky, a bit like a lighthouse. And if that beam of radio waves shines in your face, you see a pulse. If the beam misses the Earth, you don't see it. Now, pulsar astronomers working at radio wavelengths inevitably pick up a certain amount of locally generated interference. But if the interference is generated locally, it does not travel past many electrons, and all the frequencies arrive at once, and it comes in as like one of those vertical bars on that last diagram. Whereas a pulsar is at considerable distance, and as that radio pulse travels towards us, the low frequencies get delayed more than the high frequencies, and we get this descending curve, this lovely whistling curve. And indeed, by how quickly the curve drops, you can work out how many electrons the signal has come past and get an estimate of the distance. So people who study pulsars regularly make plots like shown in this diagram. There's a pair of them here. In the top two parts, you can see the pulse. And in the bottom part, you see the plot of frequency against time, and you see that light-colored curve, that descending frequency. So radio astronomers always do that. And as long as there is that nice curve descending, they know they've got a pulse from a distance, not local radio interference. So in this slide, you can see in the black corner, a very, very nice, very strong, very slender pulse. And in the yellow box, you can see this descending curve. So it's come from a distance. When you start to work out how great a distance it's come from, how many electrons it come past, it turns out that it's descending very, very slowly, which means one hell of a lot of electrons. So many electrons, well, more than in our galaxy in that direction. So it has to be from beyond the galaxy. The snag is, when you get to the edge of the galaxy, the electrons get much more thinly spread out, and you have to go one hell of a distance to make up all the electrons you need to explain that slowly dropping curve. So it's extragalactic. So is it an extragalactic pulsar? Well, they never saw another pulse from that place in the sky. And for a long time, they didn't know what to do about this. They finally published it, and people really were a bit suspicious. And for a long time, that was it. And then other radio astronomers started finding pulses a bit like this, also with the very slow descending curve, also extragalactic. And we've been finding more and more of these now. They're called fast radio bursts. They're all extragalactic. They're from where no previous radio pulsar has been seen. They rarely repeat, and there doesn't seem to be any steady radio signal either. We're just beginning to be able to position some of them. They come from other galaxies, massive galaxies, with a hell of a lot of stars, and they're located somewhere in a massive galaxy. And that's the best we could do at the moment. The next slide, please. So this is showing some more bursts. We've now seen over 3,000 of them. They're all extragalactic, redshifts between 0.5 and 1. A handful, well, maybe a few tens, are seen to repeat. For a while, the Australian radio astronomers at the Parkes Radio Telescope were seeing a second kind of burst. They found quite a few of them. They came from all over the sky. They couldn't really make sense of them. And this was a big, big puzzle. It was hugely helped when a graduate student, bless them, decided to make a plot of when these other bursts occurred, make a plot against local time. This is not something astronomers usually do, but they made a plot of the occurrence of these bursts against local time and found that they tended to occur between 12 noon and 1. What do we do between 12 noon and 1? We have lunch. There's a staff room in the observatory with a microwave oven. They tested that microwave oven. They knew it did not leak microwaves. But they discovered that if you stop a microwave oven by opening the door, not by pressing the stop button, it's a few microseconds before the microwave oven stops, and you get a chest full of microwaves. I recommend stopping your microwave using the button. And because in the microwave oven the frequencies scan down so that they cover ice and water and steam, these signals that they picked up were sweeping down. They've now taken the microwave oven away. There is no microwave oven at parks, and we have a much clearer idea, well, a somewhat more clearer idea of what's going on. The next slide, please. So we're still working on fast radio bursts. We have far more puzzles than we have solutions. It's getting to be a very hot topic. But in terms of what we now understand, there isn't much more that I can say than what I've said. There are many, many more questions than there are answers. Meanwhile, of course, there are new telescopes coming along. In the next slide. So in Canada, they have built in British Columbia, in amongst the Rocky Mountains, a big new radio telescope called CHIME. You can see 1/4 of it in the right-hand image. It's a fairly simple construction. It's designed to observe hydrogen in the universe, but it also is very good for picking up these fast radio bursts, and it's found over 3,000. It works at slightly lower frequencies than the other radio telescopes, which is interesting, but still not very good at positioning bursts. They're getting better at it, but not very good yet. In the next slide. So I'm going to leave fast radio bursts there. It's a very active area, lots of telescopes tuning into it, lots of papers, lots of discussion, not a lot of clarity or light. But clearly, astronomy is moving towards the transient phenomena, that is, not transient astronomy itself. Astronomy itself is not transient. We're going to be doing astronomy for quite a while. There's a big, big telescope building in Chile. There's a diagram of what it will look like here. You can possibly see a couple of white people. There's one on the left-hand gallery in the middle of it, and there's one, yes, where the arrow's just gone at the right-hand end of the gallery, 1 floor down. It's over 8 meters in diameter. It's just been named the Vera Rubin Observatory. I think this is the first observatory in the world to be named after a woman. Its camera will have 3 billion pixels, and the camera itself is as large as a small car. The next slide, please. It will scan the entire sky visible from Chile every few days. Going to catalogue 6 million solar system bodies, 37 billion stars and galaxies. It's going to find at least 10 million time domain alerts every night. 10 million per night. No human beings can keep up with that. It's going to have to be done with a computer, machine learning. And it aims to release data on new transients within 1 minute of the data being read out. And it will be sent all around the world to astronomers at other telescopes. In Australia and South Africa, there's a big new radio telescope to be built called the Square Kilometre Array. There are some precursors of it, both in Australia, which is what's in the photograph, and in South Africa. And these are also being used to look for transient events. The South Africans have been very clever. Their big thing is going to be called the kilometer array telescope, KAT. Sorry, that's not true. I've got that wrong, the wrong way around. The big telescope's going to be called MeerKAT, More Kourou Array Telescope, which looks a bit like the image, but isn't actually in the image. And they're already using the Kourou Array Telescope, CAT, and indeed some of MeerKAT, to look for these transient events. They have put a small optical telescope. Sorry, could we go back one? They put a small optical telescope in amongst the radio telescopes. The optical telescope is slaved to the radio telescope, so it points in the same direction, and it covers the same field of view. So if the radio telescopes pick up one of these fast bursts, the optical telescope will be able to say, saw it, or didn't see it, and help position it. And the optical telescope's called meer licht, which is Dutch for more light. Thank you. Let's move on. The final transient thing I want to talk about is the newest development in astronomy. It's gravitational radiation. Next slide, please. This image, which comes from Wikipedia, is the gravitational waves you expect from a pair of orbiting stars. You perhaps know that there's gravitational attraction between you, the floor, the computer, between you and everything around you, between the computer and everything around it. And if you move something in your room, maybe you lean back from the computer, change the distance between you and the computer. In doing that, you change the pattern of gravity in your room. And that change of pattern in the gravity has already traveled away from you and your room at the speed of light. So things moving in space change patterns of gravity and cause ripples in space-time. And that's basically what a gravitational wave is. The next slide, please. I think I will, no, I won't skip it totally. If we've got a pair of stars orbiting each other and therefore producing these gravitational waves, the pair of stars are losing energy, getting closer together, going round each other faster, and ultimately the pair merge, join together, and there's a burst of gravitational waves. Next slide, please. So this diagram shows that. This is the gravitational wave initially going round steadily. The stars get closer, it goes faster, the amplitude gets greater, and they merge. And the next slide, please. This is the pattern of the first merger detected in 2015, September 2015. And there are two observatories involved, a red trace and a blue trace. And you can see for about the first third of the trace, the two are each doing their own thing. But for about the last 2/3 of the trace, the blue trace and the red trace are in remarkable agreement. And the pattern is getting faster and bigger in amplitude. This is the merger of two objects that were orbiting each other. It turns out the two objects were black holes of about 30 solar masses each. We didn't know black holes of that mass existed. LIGO has now found gravitational radiation from a lot of objects. There's perhaps a new detection a week happening at this stage. It's become quite sophisticated. And although LIGO is shut down at the moment for an upgrade, when it comes back on again, it'll be even more sensitive and detect more things. And the next slide, please. So I have one loose end, and that is to do with short gamma ray bursts. In addition to detecting the merger of black holes, LIGO sometimes detects the merger of two neutron stars. It's now detected two such mergers. And we believe it's in the merger of two neutron stars that we get the short gamma ray burst. And this little diagram shows the two stars orbiting each other, moving closer together, and finally merging. Not only is LIGO gradually improving itself, there's another gamma ray detector in Japan called KAGRA, which will join in very soon. So we're going to get even more from that new spectrum, the gravitational wave spectrum. And it's going to be all transient events. Thank you. So transient astronomy is turning out to be very, very exciting. It's very new. It's in a very booming phase. Lots of dramatic results coming in, lots of interest, lots of puzzles, lots of excitement, and more and more and more. So thank you for your interest. Thank you for your attention. Thank you, Elvira.
And thank you very much, Jocelyn, for such a fascinating and thought-provoking lecture this evening. That was really, really interesting. And thank you, Elvira, for interpreting all of Jocelyn's speech. I'll start with one quick question that I can answer myself, which a few people have asked, which is where will this be available online? And we're soon going to be finding a platform to post all of the East Midlands Branch Institute of Physics videos. And however you found out about this lecture tonight, we will make sure that we tell everybody that we can once we've launched this platform. So it'll be on social media and out to the membership. So just keep an eye out for that platform and also for any upcoming webinars that the East Midlands branch of the Institute of Physics and the Institute of Physics more broadly might be hosting that you could be interested in. So please do post lots of questions in the chat, and I'm going to turn to a couple of questions now and put them to Jocelyn. So the first one I'll pick is a question from Jim, which is, how do you know that a transient object passing in front of a star and microlensing isn't a black hole?
You don't know that it isn't a black hole unless you can actually see it's a star. Some of them will be black holes, yes, undoubtedly. I'm sure the black holes move around the way the stars move around.
Brilliant. That's just a classic case of physics doesn't know everything. So we've got another question here from Amy. She starts out by saying, thank you very much for the lecture. Can you recommend any sources for further reading?
Whoa, not really prepared for that one. A lot of the stuff I've been talking about is very, very new. It's in scientific papers, but it's not in books. But watching things like Sky at Night regularly, reading things like New Scientist probably would be one way of keeping up. Oh, and Astronomy Now and Sky at Night and magazines like that.
Oh, that's brilliant. Thank you. So there's another one here coming from Tim. Is the microwave background dynamic? Does it change over time?
I suspect not, but I'm not a complete expert on that. I mean, obviously it has evolved with the universe, but I don't think we would see changes in a lifetime, put it that way. That's it's evolving but not changing. That's a bit.
That's brilliant. We've had lots of people thanking you for such a wonderful talk. So many people saying thank you, and I have to mention that because I want to pass on those thanks directly to you, Jocelyn. Here's a question from Jeff. Could there be any rogue planets in our vicinity?
Probably not in very near, put it that way. Because why? Because I think if there were rogue planets in the solar system, we would have noticed, we would have seen the effects of their gravity. So I think we can say pretty safely not in the solar system.
Cool, thank you. Just tracking these across. So Jocelyn, what are your hopes for the future of transient astronomy?
Wow. I suspect it's going to go on throwing surprises at us for quite a time, because it's like opening a whole new dimension. I think we've only just started exploring this, and I suspect there's a lot more to find. And particularly when that Rubin telescope in Chile gets going with its million alerts a night or whatever, we're going to find a lot of things that we hadn't dreamt of, a huge amount.
Brilliant. I've got a question here from Christina. What advice would you give a teenage girl considering studying physics or astronomy?
Well, the physics is important. The maths, you also need to be reasonably competent at maths. Those are the two most important things. And if you can keep on top of those, that's great. That's the main goal, main target. For the rest of your time, you can do what you like.
Okay, we've got a question here from Keith. Do we actually know that gravitational waves travel at the speed of light?
The theory certainly says they do. I doubt if we have measured it, but I suspect that if they didn't, we would have seen discrepancies in some of the observations we've made. You know, bits wouldn't tally properly.
Okay, we've got a question from Wakas, I think that's right. Can we visit the microscopes, the telescopes that you've mentioned?
Chile's a long way, and that one's, you know, only building. You can probably visit Palomar, that's in California. I would imagine there is a visitor facility there, but I'm not absolutely sure. Jodrell Bank, that I showed you right at the beginning, in Cheshire, has a magnificent visitor centre, and you can undoubtedly visit there. COVID regulations allowing, but okay. I don't know the situation in South Africa with Meerkat. I just don't know whether they have a visitor facility. If you're a professional astronomer and you get a time allocation on these telescopes, you may be able to visit. Although increasingly, more and more, you don't visit, you do the observations remotely.
Yeah. Cool. So I'm going to combine a couple of questions here, and this is sort of what repercussions will transient astronomy have for related areas of astronomy, in terms of could it affect the cosmological constant, and could it say anything about dark energy or dark matter?
I think all the transient stuff we have observed so far is probably relatively nearby. For instance, the fast radio bursts, I don't think we've seen any at a redshift greater than 1, and that's local, you know, in terms of the universe. So I'm not sure. Well, it does really depend what transient things we find in the longer run, but as we stand at the moment, all the stuff we're seeing, we believe, is relatively local. You know, on a logical scale.
Thank you. There's another question, sort of with again your personal take on this. If there was one transient astronomy project that you could be involved in, what would that be?
I think it would be the fast radio bursts. And although I'm not actually involved in it, I'm pretty close to it because I've got radio astronomers around me, at least when we're at work. So, not during lockdown.
We've got a few questions here about finding life on other planets or other galaxies. Do you have any comments about that?
I think going to other galaxies is, finding life in other galaxies is going to be tricky. but we are discovering more and more and more planets. If you look up at the night sky, not sure if it's still clear, but if you look up at the night sky, you see lots and lots of stars. You should say to yourself, there's as many planets up there as there are stars. We're now finding so many planets. And with so many planets, and the numbers growing very fast, maybe one day we'll find a planet which is habitable or maybe even inhabited by some sort of life. But we haven't yet, and I don't think we're quite there yet either.
Brilliant. I've got a question here. Do we know how rogue planets form?
Probably rogue planets form the same way as any other planet, but then for some reason they get detached from their parent star. They become orphaned. And it may be if another star comes along and disrupts the planetary system of the first star, which could happen. And that leaves these free-floating or rogue planets.
Brilliant. We've got a few questions around if you could give either past you or advice to a young scientist growing up now, what advice could you give?
I'd say go for it. The world needs scientists, all sorts of scientists. If you've got a bent for science, do it. Do keep up your maths as well, because not only in astronomy, in many fields there's lots and lots of data, and you often have to use statistical methods, so you need your maths as well as the science.
Brilliant. Definitely a theme there, that there's so much maths going on with this. How can one tell whether an orphan planet is a distant planet which has become detached from a parent star system, or is a protostar which hasn't ignited?
I'm not sure I know the answer to that. The planet would be physically smaller in dimension, in size, more compact probably than a protostar. I'm not sure I can answer that one neatly.
No, that's brilliant. Thank you. Very honest with you. So I've got a couple of questions about the timescales that these kind of astronomical events happen on. And I guess one to pull out specifically, how long does it take for a pair of binary stars to collapse?
Well, it does depend how far apart you're starting from, you know, where you start the clock. But the final merger, the gravitational wave bit, is a matter of 20 minutes, something like that.
Gosh, that's much faster than I was picturing, certainly.
Well, that's just the final bit, the spectacular bit.
How much has the advancement in new information technology, such as artificial intelligence and machine learning, impacted observational transient astronomy?
It's getting, it's sorry, it's being used more and more and more and more and more. Its growth is increasing enormously. One of the problems with a big data, well, there are many problems with a big data set. One is that no human being can manage it. It has to be done by machines. The other big problem with a big data set is you can't really ship it anywhere. You've got to analyze it where it's taken. So not only do you build a big telescope in Chile, you build a big computer suite as well, with all the air conditioning and all the stuff that needs.
Brilliant. And I guess to follow on from that, what sort of, other than just making things possible that wouldn't have been as possible before, what sort of things have you found using that new facility?
Well, the one in Chile is still building, it's not ready yet, but the one on Mount Palomar in California is showing us that there's a far, far greater variety of things in the sky than we had dreamed of. And our old, nice, neat classifications are being busted over and over and over again. Really, really interesting time. And, you know, phenomena like fast radio bursts that we had never dreamt of, lasting a tiny fraction of a second. Amazing.
Brilliant. Can you describe what the technology looks like or is similar to that is used to detect radio waves?
Radio waves, radio telescopes, often they're big dishes, which are actually the collectors, with a very small receiver, radio receiver at the focus. Longer wavelength radio telescopes are more like strands of wire strung up. They're rarely dish-like, if I could put it that way. But there's a low-frequency radio, low-frequency radio telescope in Europe called LOFAR, which is, you know, there's a bit in Ireland, there's a bit in England, there's some in France, there's lots of bits in the Netherlands. You know, it's in patches all over the place. And that is low frequency, but apart from that, most radio astronomy has moved to higher frequencies. And so you're thinking in terms of these dish reflectors and the actual detector at the focus of the dish.
That's really helpful, thank you. Got a question here. Will a newly formed neutron star inevitably be a pulsar, or is it possible that a neutron star might not become a pulsar?
To be a pulsar, it has to have a strong magnetic field, and the magnetic field has to be misaligned with the spin axis. In other words, the magnetic field is not along the spin axis, but inclined to it. So you can get many, many neutron stars, I suspect, that are not pulsars.
Okay. What has been the most rewarding or exciting part of your career?
Well, obviously discovering pulsars as a grad student, but that was over 50 years ago. I would think now, certainly this transient stuff, and for me, I think the fast radio bursts, because it takes me back to the radio astronomy.
Brilliant. Are there such things as rogue stars or rogue galaxies?
There might be. I've not heard of any labelled as such. I'm sure some researchers might be tempted to label the star or galaxy they're observing, trying to understand, as rogue, but I don't think it's a regular terminology.
Okay. How has the advancement of our knowledge in transient astronomy impacted fields such as grand unification theory?
So far, I would say there's very little impact outside of astronomy, but that's partly because we're still a long way from fully understanding what these transient things are and why they're doing what they're doing. So as we get more understanding of this new field, there may be impacts in other areas.
Okay. So you talked about different parts of the electromagnetic spectrum having events in them. Are there parts of the spectrum where there aren't events, where they don't occur?
We suspect not. There are some parts of the spectrum, like the ultraviolet, which at the moment is not terribly well covered. You need to have your ultraviolet telescope on a satellite above the Earth's atmosphere, and you can be between satellites for a while. There is some capability up there, but I think there's not great ultraviolet coverage at the moment. So dear knows what's going on in the ultraviolet.
We've got another slightly non-technical question. What is it like being a woman in physics?
A minority, but the minority is getting bigger quite rapidly now. It's really interesting. with a lot more women around than when I was student age. So I think it's getting easier and easier for there to be women in physics, in astronomy, because there are more women. And the subjects, of course, remain as exciting as ever. So they're great fields to be in.
Brilliant, thank you. So there's a question here referring to some recently published research indicating that a fast radio burst was detected from within the Milky Way.
Mm-hmm.
Do you have any,
Yeah.
Can you explain that for the audience that aren't aware of it, and what do you think of it?
Yes, there is a recent report of something that looks quite like the fast radio bursts I was talking about, coming from a kind of neutron star called a magnetar within our own galaxy. And people wondered if this was related to the fast radio bursts. I'm not sure that it is. It's many, many factors of 10 weaker than the normal fast radio bursts coming from distant galaxies. Might be related. It's a bit hard to know. It's a bit new.
Okay. Do you think that the public now has an understanding or excitement for your field and for science? And I guess how has that changed up till now?
I think astronomy as a branch of science has always proved very attractive to people outside the field, to the general public, if I can label people as that. And I think I think that's good, because one can therefore use astronomy to explain some basic physics to people and help their understanding of physics. There's also interesting developments in physics, you know, things being done with the accelerators in Switzerland. Lots of fundamental experiments going on, lots of interesting technical developments as well, which maybe lead to better widgets or better computers or better something. A lot going on.
Brilliant. Is there any risk from something like a rogue planet entering our solar system in the future?
Well, we now have telescopes, and the one that comes immediately to mind I showed in an earlier slide, the Atlas telescope in Hawaii, which is specifically looking out for things that might come and hit the Earth. Along with that, of course, it also picks up objects that flare and dim, you know, the transients that we're also interested in. But its main purpose is spotting killer asteroids.
Brilliant. Will the increasing use of low orbit microsatellites interfere with our ability to detect these kinds of things?
They will interfere, yes, badly in many, many ways. It's could be a disaster, a catastrophe, both in the optical and in the radio. It's very, very concerning.
There was been a couple of questions about the impact of transient astronomy and the phenomena that you've described on other missions. So I guess I'll try and pull them all into one and say what other areas of science will this impact mostly on?
I don't think transient astronomy will impact on missions in the sense that they'll have things to look at. It will not literally impact in the sense of things coming and hitting satellites.
No.
I want to
yes,
be clear.
I meant on the knowledge of the field, yes.
Yes, okay. Opening up a new window like this always produces, first of all, a great surge of excitement and a surge of data. And then as we get to grips with it, we find we have to perhaps revise our understanding of things we thought we had, you know, kicked off. So it can have impacts beyond just what you think the impact might be. It's interesting. But with the transient field, we're still at the stage of gathering, cataloguing, classifying, and trying desperately to understand. And, you know, impacts on other fields are still a little bit downstream.
Okay, that sounds very familiar from all sorts of areas of physics.
Yes.
So there's a few questions talking about gravitational waves and your thoughts on gravitational wave detections, and then potentially how that impacts on discovering of the graviton or something like that. So if you could perhaps talk us through some of that, please.
Yeah. The gravitational wave detectors that we have at the moment, which are doing a brilliant job, are fairly low frequency ones. No, they're at the right hand end there. Anyway, they're in a limited range of frequency. To get the adjacent bands and slightly different kinds of objects detected, we're going to have to go to space. And there are things developing quite fast now to put up maybe 3 satellites that together will work as a gravitational wave detector. And of course, also we have dotted throughout the galaxy some quite useful ticking things that behave a bit like very good clocks. They're called pulsars. And if you're observing pulsars and you see a group of pulsars in one patch of the sky all change their period a bit, it's probably because the space there has been distorted by a gravitational wave. So we can also use pulsars to detect gravitational waves. We haven't quite got the sensitivity yet. We haven't quite got found the pulsars that are reliable enough, but we're heading that way. So the gravitational wave astronomy will expand through its spectrum over the next few decades. And this is a whole new spectrum, quite separate from the electromagnetic one with the radio and optical and X-rays and so on.
Thank you. That's something to really look forward to and keep an eye out for. So I have one final question, I think, and then we'll draw the evening to a close. What was it about physics that attracted you into the field so much?
I could do it. It was easy. I was very lucky in the very first physics exam. I got a very high mark and came top of the class. This was at about age 12. You know, and it's often the case that you like the things you're good at. And so I was hooked on physics right from as soon as I started doing it. So I'm sorry, she's a real nerdish.
No, that's brilliant. That's a real insight into your experience growing up as well. So thank you so much, Jocelyn, for a wonderful lecture and for answering all of our questions. And thank you, Elvire. And do keep in touch with the Institute of Physics. Hopefully there'll be more webinars in the future that spark your interest.
Thank you.